Okay, we are on to the second linear application problem, and this one's going to talk about Grandma McGregor and her cookies. So hopefully you can just smell that nice scent of warm baked cookies coming out of the oven right now. Sometimes the cookie dough is just as delicious. You don't even need to bake them. Make sure you can get the cookie dough that's ready to eat though, without the raw eggs in it. All right, this question says, Grandma McGregor loves to bake her grandson cookies and brownies. On a Sunday afternoon, Grandma McGregor finished baking a batch of delicious cookies, and then she shuts off the oven. She left the oven door open so it would cool down faster and also warm up the house. That's a little tip to saving money. If it's in the winter and you cook something, just open the door when you're done cooking something in the oven, and that heat will escape and heat the house a little bit, so it saves you on your heating bill. 10 minutes after turning the oven off, the temperature is dropped to 300 degrees, and 14 minutes after turning the oven off, the temperature has fallen to 250 degrees. So as more time goes by, the temperature is going down. The temperature of the oven varies linearly with the amount of time that passed. That just means the temperature is going to go down at the same rate. So first, let's start with some coordinates. So we know that 10 minutes after turning the oven off, the temperature is now 300 degrees. Let's write that as a coordinate. We know that 10 minutes, remember time is usually the x-coordinate. The temperature is about 300 degrees. Now in the next sentence, it gives you another point that you can write. After 14 minutes, the temperature has fallen to 250 degrees. Let's write that as a coordinate. After 14 minutes, the temp is now 250 degrees. Now we're going to do the ever so important step of defining our terms. So the x-coordinate, that's your first one, this 10 and 14, that represented the minutes since the oven was turned off. So she finishes baking the cookies and then she turns the oven off. That's when we start the timer. And then the y-coordinate, so if we look here at the 300 and the 250, those are the y-coordinates, and those both represent the temperature of the oven. Temperature of the oven, and these are probably going to be in degrees Fahrenheit. If you had 300 degrees Celsius, you'd probably burn the cookies. So these are in degrees Fahrenheit. Part C says calculate the equation of the line that represents the temperature of the oven after a certain number of minutes. So this is just saying find the equation of that line. So we're going to start with y2 minus y1. So that's going to be 250 subtract 300 over x2 minus x1. That's going to be your 14 minus 10. And we get negative 50 over 4. And this one specifies to convert your slope into a decimal. So I'm going to take negative 50 and divide it by 4. And we get negative 12.5. And that is my slope of this equation. Just to kind of remind you what this slope means. The negative 50, that's the change in y. The 4, that's the change in x. So the temperature is changing by 50 degrees. It's going down by 50 degrees over a span of 4 minutes. And we'll interpret that a little bit later. But it went down 50 degrees, and it took 4 minutes to do that. Next, what we're going to do is we are going to use y equals mx plus b. And we're going to plug in some information that we know. So you can pick either of the 2 points. I think it's probably a little easier if you select this one. So in for the y-coordinate, we can replace it with 300. So the y becomes 300. M represents the slope, and in this case, the slope is negative 12.5. The x, if we go back to that point, the x-coordinate was a 10. So we're going to replace x with 10. And then we have plus b. We're trying to solve for b. We're going to simplify next. So we get negative 12.5 times 10 is negative 125. And then, finally, if we are trying to get b by itself, let's move that minus 125. We're going to plus 125 to both sides. And that gives us a b value of 425. There's your y-intercept, 425. Now you're not done. We actually need to write the final equation. So your final equation would be y equals negative 12.5x. So whatever your slope is, put it there next to an x. And then your y-intercept is plus 425. And this is the final equation that is modeled by this scenario. And we're going to be using that for the rest of this problem. So again, make sure you understand how to find the equation of that line. Part D says, what is the y-intercept of your equation and what does it represent? So the y-intercept is this one right here. And I'm going to write it as a coordinate, 0, 425. And remember, 0 is the x, 425 is the y. Let's remind ourselves what x stands for. X is the minutes since the oven was turned off. So 0 minutes have gone by since we turned that oven off. And the y represents the temperature. It was 425 degrees. So essentially, right when the oven was turned off, 425 degrees. So essentially, these cookies were baking at a temperature of 425 degrees. When she took them out, she turned the oven off. So that's times 0. So when the oven was turned off, it was 425 degrees. So remember, we've mentioned before that the y-intercept is kind of like your starting point. So the oven starts at 425 degrees, and then it's going to be going down from there. For part E, it asks, what is the slope of your equation, and what does the slope represent? So I'm going to go back to this fraction, where we had negative 50 over 4. So the temperature is decreasing by 50 every 4 minutes. But then we divided it. And so what dividing does is, instead of going over 4 minutes, it's just taking it over 1 minute. So when we divided this and we got a negative 12.5, that's what's happening each minute. So the slope is negative 12.5. And typically a good word to use when you're describing the slope is the word each. So I'm going to say each minute the temperature of the oven now, is that temperature going up or down? Well, if the slope is negative, that means it's going down. So I'm going to use the word decreases by 12.5 degrees. So each minute, it's going down 12.5 degrees. If you wait for 4 minutes, it's going to be going down by 50, and that's what we saw with the fraction earlier. But each minute, down by 12.5 degrees. And calculate the x-intercept of this scenario. What does the x-intercept represent in the real world? So remember, to find an x-intercept, let's start with our equation. Anytime you want to find an x-intercept, all you have to do is replace the y-coordinate with 0. So let's replace this with a 0. And then we're going to solve. So we're going to get rid of that 425. So let's subtract it out. And we get negative 425 equals negative 12.5x. Now if we're trying to solve for x, we still have to divide, so let's divide by negative 12.5. And I believe we get 34. Let me double check. So 425 divided by 12.5, 34. So we get x equals 34. Remember, it's easier to interpret if you write it as a coordinate. So the x-intercept is 34, 0. And let's try and interpret what this means. The x represents the minutes, and the y represents the temperature. So after 34 minutes, the temperature of the oven has now gone to 0. Let's try and think of that. Think of what 0 degrees feels like. Do you think an oven is going to get to 0 degrees? No, that's colder than your refrigerator. What's happening is, I'll just give you a little sketch. The temperature is starting at 425, and what it's saying is after 36 minutes, or 34 minutes, sorry, after 34 minutes, the temperature would go to 0. That's not actually going to happen in real life. What's going to happen is it's going to start at 425 and go down, 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 down until you get to room temperature. And room temperature would be probably 75 degrees. And then it would actually flatten out and look like that. So the x-intercept in this case is unrealistic. So I'm going to say it's unrealistic in the real world because that won't happen. You won't have an oven that goes down to 0 degrees. So sometimes your model breaks down and you can't use it for all sets of data, and that's fine. For part G, we're going to go through these next two pretty quickly. What's the temperature of the oven 23 minutes after it turns off? Start with your equation. Y equals 12.5x plus 425. And now it's saying that we want to know the temperature of the oven 23 minutes. Is that minutes an x-coordinate or a y-coordinate? Minutes was the x-coordinate. So I'm going to replace the x with a 23. And then we're going to take that 12.5 and multiply it by 23. We get a negative 287.5. So we just simplify that. And then we can simplify one more time. We get 137.5 degrees. So what this means is after 23 minutes, the temperature is 137.5 degrees. And one more last question. How many minutes will it take until the temperature cools down to 150 degrees? So let's once again start with our formula. And in this case, what's given to you in the problem is they're giving you that temperature, 150 degrees. The temperature is the y-coordinate, so let's replace the y with 150. And then we're going to subtract the 425 from both sides. So if we subtract 425, subtract 425, that gives us negative 275 equals negative 12.5x. And then we have to divide by negative 12.5. And we get an x value of 22. What that means is, after 22 minutes, the temperature has cooled to 150 degrees, which is what was asked for in the question. So hopefully this was starting to make sense. Hopefully you're starting to get the hang of it. go ahead and create the graph and put the screenshot, and then you're set for this problem.